Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us begin solving this step by step. Identify the starting material. The starting material is acetaldehyde, CH3CHO. Moving on to the next step. Reaction with HCN. HCN adds across the C is equal to O of acetaldehyde in a nucleophilic addition to give a cyanohydrin, CH3CH, or -CN. This is compound A. Moving on to the next step. Hydrolysis with H3O+. The nitrile group, -CN, in A, is hydrolyzed under acidic aqueous conditions to give an alpha-hydroxy acid, CH3CH, or -ChO. This is compound B. And for the final step. Heating delta. When an alpha-hydroxy acid is heated, it undergoes dehydration to give an alpha-beta-unsaturated acid. From CH3CH, or ChO, elimination of water gives CH3CH is equal to CHCO, but 2-enoic acid crotonic acid or its isomer. This is compound C. Compound C has the structure CH3CH is equal to CHCO, which can show geometrical cis trans isomerism because of the double bond between two carbons each bearing different substituents. This confirms the clue given in the problem. Reduction with Lyell-4. Lyell-4 reduces both the C is equal to C double bond and the ChO group. Actually, Lyell-4 selectively reduces the carboxylic acid to a primary alcohol while leaving the double bond intact, or reduces both. More precisely, Lyell-4 reduces ChO to CH2O without affecting isolated alkenes typically, but with conjugated systems it can reduce both. However, for this problem we need compound D that upon HiO4 oxidation gives HCHO plus E. HiO4 cleaves vicinal diols. So, D must be a 1,2-diol, vicinal diol. This means Lyell-4 reduces the C is equal to C as well, giving a diol. Actually, Lyell-4 reduces the ChO to CH2O giving CH3CH is equal to CH2O, but that doesn't have a diol. Re-examining if C is CH3CH or CH is equal to CH2. No. Let's reconsider if dehydration of CH3CH or -ChO gives CH3CH is equal to CHCO, crotonic acid, then Lyell-4 reduction gives CH3CH is equal to CH2O, but 2N1-ol. This doesn't have a vicinal diol for HiO4 cleavage directly. However, HiO4 can cleave compounds with a double bond if they are first. Actually, revisiting, Lyell-4 reduces CH3CH is equal to CHCO to give CH3CH is equal to CH2O. But HiO4 cleaves 1,2-diols. For HiO4 to give HCHO, one carbon must be CH2O on one end. If D is CH3CH or CH or CH2O, a triol after some other process, that would give HCHO plus CH3CHO plus HCHO. Let's reconsider, perhaps the dehydration gives an unsaturated acid, Lyell-4 reduces to unsaturated alcohol, then HiO4 oxidize the double bond directly. HiO4 can cleave alkenes via osmium tetroxide first, but alone it cleaves diols. More likely, Lyell-4 reduces both the double bond and the acid giving CH3CH2CH2CH2O, but that gives no HCHO with HiO4. The most consistent interpretation, C is equal to CH3, CH is equal to CHCO, D after Lyell-4 is equal to CH3, CH is equal to CH, CH2O, and HiO4 cleaves the double bond, treating it as periodic oxidative cleavage of the alkene, analogous to ozonolysis context in some textbooks giving HCHO from is equal to CH2. No. Actually, if D is equal to hot to CH or CH or CH3, after the hydroxylthione then reduction, HiO4 cleavage gives HCHO plus OHCCH or CH3, then further cleavage gives HCHO plus CH3CHO plus HCHO. The answer, E, is equal to CH3CHO is equal to option C. With HiO4 cleaving vicinal diol of CH3CH or CH or CH2 or cleavage between C2, C3 gives CH3CHO plus OHC, CH2O, and OHC, CH2O further cleaved gives HCHO plus HCHO. So one product is HCHO given and E is equal to CH3CHO. Option C, CH3CHO matches. Therefore, the correct answer is C. Therefore, the correct answer is option C.